So what we have here is a notation that, again, as you continue in math, you're going to see for a long time. This is called sigma notation. That's what this letter is. This is a Greek letter sigma. And it's based off a sequence. This is our A sub k's like we've been working with. And all it means is that we are going to add up all of these pieces. So I'm going to write down, so this piece is called sigma. This is sigma notation. And what it means is that we're going to start at this bottom value. So we're going to start when k equals 1 in this case, and most times, but not always. And whatever this number is up here is going to be where we stop. So if we're starting at 1, we're going to add together all of our a sub k's until we get to m. So we're going to start at 1 and do a sub 1. Then we're going to do a sub 2. Then we're going to do a sub 3. And we're going to add all of them up until we get to a sub m, whatever that last value is. These are called partial sums because we usually do these upon infinite series or infinite sequences. So it is a partial sum. We're adding up a part of it. So that's what we're going to do today. Is we are going to find the sums of sequences within certain ranges. So I'm going to change the page. So our first one's going to look like this. What we have here is, we have our rule. This is the rule we're going to work with, just like it was yesterday. This is where we start. So we're going to start at 1. And we're going to end at k of 4. So this is our end, where we stop. So if I'm going to start with 1 and end with 4, how many pieces are we going to add together? 4. Because we have k equals 1, and we're going to calculate that. We're going to calculate k equals 2 and calculate that. We're going to find k equals 3, and we're going to calculate that. And we're going to calculate k equals 4. So we're adding up from 1 to 4. And what we're going to do is we're going to run this k equals through our rule. So if k is 1, we're going to substitute it in. So I'm going to take my 1 squared times 1 minus 3. Substituting in the pieces. Well, 1 squared is 1, bless you, times 1 minus 3 is negative 2. So k equals 1 has a value of negative 2. We're going to do the same thing for 2 and 3 and 4. We're going to find the values.
So you just leave it like that as a thing?
We're not there yet. Like, I'm going to take all these values and do a thing at the end, okay? So I'm just writing them out kind of next to each other. So I'm going to substitute them in because we're going to have our 2 squared times 2 minus 3. It's going to give me 4 times negative 1, also known as negative 4. Again with the 3, same process. 3 squared times 3 minus 3. So we have 9 times 0, also known as 0. And then our last one up here for 4, same thing. 4 squared times 4 minus 3. So we have 16 times 1, or 16. So we have found our a sub k for k's 1 through 4. That's the same kind of thing we did yesterday. We just were finding the values. What the sigma means we need to do, so what he means, is I need the sum of these pieces. Sum is another math word for what operation? Addition. So we're going to take our k of 1 and add it to k of 2. Add that to our k of 3. Add that to k of 4. So we're going to add together all of these pieces. When we sum them up, what do we get as the total sum? What is -2 plus -4 plus 0 plus 16? 10. So the sum from k is 1 to 4 of our function rule, k squared times k, that's k, minus 3 equals 10. That's the full way to write it. I know I'm super close to the bottom there. Questions on this one? So it's super impressive looking and really kind of scary looking, but it means substitute and add. Okay, let's do another one. So we're going to find the following sum. So we've got the sum from k equals 0 to 5. And that's the order that we read it in, as we say the sum, that's our sigma, from the bottom to the top. So the sum from 0 to 5 of 3 times 2 to the k. So if I'm starting at 0 and going to 5, how many things are we going to add up? How many terms are there going to be? 6 terms. So this is going to have 6 terms. That's helpful when we're planning out our spaces to think about how many terms it is. Because if I only have 3, I can take up a lot more space. If I have 6, we're going to be very tight on our space. So I'm going to substitute all those pieces in. I'm going to start at my starting point. We start with 0. So this is my start. I'm going to come all the way to the left, and I'm going to start with k equals 0. And we're going to substitute it into our rule. Our rule being 3 times 2 to the 0. Well, 2 to the 0 is 1, exactly right. So this one is just 3. Then I'm going to do my next term, k equals 1. Same thing, substituting it in. 3 times 2 to the first, which is going to give me 3 times 2, also known as 6. We're going to just keep going, filling in our pattern here. K equals 2 we're going to do our 3 times 2 squared, also known as 3 times 4, also known as 12. Keep it going. We're not stopping until we get to 5. So we're going to do our K of 3. And this is going to have 3's everywhere. So we have 3 times 2 cubed. Well, that's the same thing as 3 times 8. So we have a 24. Almost there. We're at K of 4. Same vibe. 3 times 2 to the 4th. Going to be 3 times 16. Also known as 48. And then we're finally up to K equals 5. So we're going to have 3 times 2 to the 5th, which is 3 times 32, which is going to be 96. So I'm finding all of my values, all of my A sub K. Then we're going to remember that the sigma means the sum. So we're going to take all of these pieces and sum them up. So we're going to take 3 plus 6 plus 12 plus 24 plus 48 plus 96 and sum them all up. What do we get when we add all of those together? 189. So again, I'm going to write the whole sentence just so that we get some practice writing all these things. So we say that I'm going to make this a little bit thicker. The sum from K equals 0 to 5 of 3 times 2 to the K equals 189. And your sigmas don't have to be pretty because, I mean, totally mine are. They're gorgeous. It looks like a sideways M, but it gets the point across. Questions of these? Okay. We're going to do a couple more like this. Same vibe. Same vibe. We're going to do the sum from 0 to 6 of 3j plus 2. So how many terms are we going to have? 7, because we're starting at 0 and stopping at 6. So we're doing 0 counts as well. So we're going to have 7 total terms. So we're just going to figure those out. We're just going to start and truck along. So when j equals 0, what is the value? 2, because it's 3 times 0, which is 0 plus 2. When j is 1, 5. 3 times 1 is 3, plus 2 is 5. That's why it feels so chunky. I left it chunky. J of 2, 8. J of 3, 11. So you don't necessarily have to write every single molecule of every step out. If it helps you, absolutely write it out. But I also, at this point in your math careers, I'm pretty sure y'all can multiply in your head for the most part. So, like, I am 100% okay with us doing this with mental math. So J equals 4. It's going to be what? 14. J of 5. 17. And J of 6. 20. So we're going to need to sum these up. Add them all together. 2 plus 5 plus 8 plus 11 plus 14 plus 17 plus 20. Whew. What do we get as the total for our sum? Yeah. We're going to have 77 as our total. Okay, so again, I'm going to write the whole thing out as our answer again. So we're going to have the sum from J equals 0 to 6. And again, that's the order we read it in, is the sigma from J equals 0 to 6, bottom to top, of 3J plus 2 equals 77. So that's the way I would write that as a solution. Questions on these? They look super complicated and they look super duper showy. The math in them is not hard, but it looks scary. Okay. One more. So we're going to find the sum of the sequence from K equals 1 to 6. So we're finding the sum from 1 to 6 of 3 over x plus 1. So how many terms are we going to have? So we're starting with 1. This always tells us our starting point on the bottom. So we're starting with K equals 1. And it's going to give us what value? 3/2. 3 over 1 plus 1, or 3 over 2. K of 2 gives me 3 over 3. K of 3 Yep, 3/4. K of 4. 3/5. K of 5 is 3/6. And last one, K of 6 is 3/7. Exactly right. So we've got all of our values here. Now we're going to come through and we're going to try and add them together. When we're adding fractions, what do they need to have? The same denominator. So that's what I want you guys to do. I want you guys to try this out on your own real quick. See what we remember about adding fractions. It's been a hot second. So I want to give you guys a chance to try. Like, we have plenty of time. Try. See if you can figure out what denominator we're going to get this to. That's your first thing. Huh? You can absolutely do it in parts. Totally fine. You do not have to do it as one gargantuan thing. Because it doesn't matter what order we add things in. We should wind up at the same answer anyway. What did we get as an answer? Is anyone there yet? Totally fine if you're not. So what do we get? It's possible. Shouldn't be a 5 on the top. Definitely not. What else we got? Anybody else got something different? Should wind up, because we're going to multiply. So like if we just did it in parts, kind of like Belty said, we could take these two, and to get them to a common denominator, I need to get them to be 6. So I need to multiply this one by 3 over 3 and this one by 2 over 2. So we would have 9/6 plus 6/6. So So this piece alone would be 15/6. And you can keep going like that. You can get to a single common denominator for all of them. If you do it all in one piece instead of in little chunks, our lowest common denominator, we take all the pieces that don't have shared factors, so we'd have, you know, the 1 times 2 times 3, actually not 1, 2 times 3, so those are our first two denominators. Well, 4 already has a 2 in it, so we're going to do another 2. 5 times 6, I already have the 3 and the 2 pieces in there, so 7. So our least common denominator would actually be 420. Which if we get everything to have a denominator of 420, we're going to wind up with 2007 over 420. But that actually does simplify because both of those are divisible by 3. Yep. 669 over 140. Okay. So sometimes with these sums, we get into like pedantics, like algebra 1 stuff, where we have to add fractions. So it's good for us to remember how to do that. In part, it's like you would just keep going until you get all the parts put together. So for like the 4 and the 5, we'd get to a common denominator of 20. For the 6 and the 7, we could get to a common denominator of 42. And then we just keep going. We'd take the 6 and the 20 and combine those together. Mm-hmm. And yep, you could also push that 3 and the 6 in there. Yep, absolutely fine. Yeah, you can do it in all kinds of pieces because it doesn't matter what order we add things in. Addition is associative, so we can move it around however we want it to. Or addition is communicative. So you can do them in whatever order you want. If you want to take the 4 and the 7 and get a common denominator of 28, totally fine. If you want to take the 2, 3, and 6, great. If you want to take the 5 and the 7, go for it. It doesn't matter. As long as you add all of them up together, you should wind up at 669 over 140. Okay, you can also, you know, use the fraction button on the calculator. I didn't. Y'all making your lives harder than you need to, but that's okay. All right, so that is actually our hardest one of the day. And that's also the last one of the day. You guys have almost 15 minutes where you can work on homework. We can work on catching up on stuff. If you want to look through things, you can. If you want to ask questions, you can. If we want to chill because it's Friday and our brains are goo, I get that. My brain is also goo today. I'm tired. And I don't have prom this weekend. Yes, dear.
Do you think I can take the class with you?
Yeah.
I just have some questions.
Mm-hmm.
On this one, I think.